Bismillahirrahmanirrahim. If you recall, a deductive argument is when you take an initial premise or some given information and from there you put forth a logical sequence of conclusions. If A is given or if A is a information that's given to you, then from that you can derive B, from there you have C, and from there you have various different consecutive conclusions like this. So a deductive argument is a logical chain of statements linking an initial statement or given information, an initial premise. Here I have labeled that as A. This would be the initial premise, and from there you derive a logical sequence of conclusions to arrive at a final conclusion, and that in this case is D. A particular deductive argument can be 1, 2, 3, or hundreds of steps like this if needs be. So this is an example of a deductive argument. In geometry, we have different types of such deductive proofs or arguments, and you can diagram them to allow people to understand your thinking more clearly. So proofs in geometry are of various different types. There are two that we're going to talk about today. Today we're going to talk about flow and paragraph proofs. In the future, we'll talk about a two-column proof, which is in fact the most common type of a proof that we're going to use. But today I shall introduce you to flow and paragraph proofs. But before we do that, I just wanted to review these concepts, these properties of real numbers that we talked about last time. So these are properties of real numbers. Okay, now this is particularly important because these properties will show up in different forms in the future, so it's particularly important to know these really well. So we had the addition property of equality for real numbers, and subtraction property of equality, multiplication property of equality, and division property of equality. That's easy enough to remember. And then the reflexive property of equality, symmetric property of equality, transitive property of equality. And finally, the substitution property of equality and the distributive property of equality. Okay, these are very important to memorize, in fact. So you should be able to articulate these properties with reasonable confidence like this. Addition property of equality is that if A is equal to B, and this is for real numbers, if A is equal to B, all right, you can simply, I just put this like arrow, then A plus C is equal to B plus C. Now you can write this in a sentence form as well. If A is equal to B, then A plus C is equal to B plus C. That's the addition property of equality. Subtraction property of equality is very similar. Of course, if A is equal to B, then A minus C is equal to B minus C. In a similar way, the multiplication property of equality, if A equals B, then A times C is equal to B times C. And finally, the division property of equality says if A is equal to B, from this will flow that A divided by C is equal to B divided by C. And here, if you recall, we must add that C cannot be 0 because division by 0 is not defined. So this is a very important fine print, so to speak, or a proviso for this particular property. So addition property of equality states that if A equals B, then A plus C equals B plus C. And the subtraction property, multiplication property, and division property are very similar in conceptually as they are written. Now, these others might seem very simple or basic to you, but they're very important and very useful. Reflexive property of equality says that a number, in these cases, these are all properties of real numbers. In a reflexive property of equality says a number is equal to itself. A is equal to A. Now, symmetric property of equality is slightly different. See, a symmetric property of equality says if A is equal to B, all right, then B is equal to A. In other words, there you can like flip these around like that. If A is equal to B, then B is equal to A. I'm using these arrows to substitute for the word then, because I just find it's just easier to write it that way. If A equals B, then B equals A. The transitive property of equality is perhaps one of the most often and commonly used, and states that if A is equal to B, all right, and B is equal to C, then A is equal to C. If A is equal to B, B equal to C, then A is equal to C. So in transitive property of equality, you have to understand that you have to have something common, a bridge. If A has to go to B and B has to go to C, so they have to overlap. So A equals to B and the B equal to C, they have to overlap like this to you be able to use the transitive property. If A equals B, and B equals C, then you can say that A and C are related. A equals to C, like this. So that's the transitive property of equality, and it's very important to be able to articulate that one as well. And finally, substitution property of equality says that if A is equal to B, then A may be replaced by B in any equation of expression. If A is equal to B, then I'll use my arrow again, then A can be, that's N, A can be replaced or substituted for B in any expression or equation. Now these are all properties of real numbers, okay? So if A is equal to B, then A can be substituted anyway. And finally, if the distributive property of equality, you probably also are familiar with this. A times the quantity B plus C. Now whenever you have parentheses, it's important to say that the word quantity, because then you say everything that follows after the statement. So A times the quantity B plus C is equal to A times B plus A times C, like this. All right. So addition property of equality, subtraction property of equality, multiplication property of equality, division property of equality, and then reflexive symmetric transitive property of equality, substitution, and distributive property of equalities. It is imperative to know these extremely well, because as I said, these will come again and again in various different forms. Okay, so here's an example of a flow proof. So here we're asked here to prove that if 2 times the quantity x plus 5 minus 3 equals 13, then x is equal to 5. And we are asked here to write a flow proof. So what is a flow proof, and how do we go about writing a flow proof? A flow proof is basically diagramming your steps. So you start with the given information and you go through basically a series of deductive conclusions like this, and at each step you provide your reason. So you start with the given information over here, and you manipulate that information into logical reasoning and get the information that we have to come up with certain conclusions to the eventual result into what you are trying to prove, that which you have to prove. In this case, you want to prove that x is equal to 3. So you start out with given information and you come to the conclusion over here, or whatever you're trying to prove, through a series of steps. And what you do is you draw a diagram, like, then you can rectangulate each particular step to make it look prettier, and then you provide each reason below. So reason for every step is given like this. So reason for this, reason for this. So reason for this step is over here, reason for this step is over here, etc. For whatever you do, you have to provide a reason like this. Okay, there may be more steps in this particular proof than here. So this is an example of a flow proof. A flow proof basically diagrams your thinking and forces and requests you, or requires you to write the reasons behind every particular step. So the first thing you do in a flow proof is that you write the given information and you write what you have to prove. So in this case, we are given this particular equation. So let's write that as a given information. So we are given that 2 times the quantity x plus 5 minus 3 is equal to 13. That's what's given, and we're required to prove. If that is given, then we are asked to prove that x is equal to 3. So the first step in writing a flow proof is to write the given and information and what we are required to prove. And then we write the flow proof. Here is the flow proof. So when in doubt, it's a good rule in geometry just to actually start from the given information. That's generally where you always need to start anyways. So 2 times the quantity x plus 5, okay, minus 3 is equal to 13. So you start out with the given information. And here I am going to this is what I call this the rectangulating, putting them in a box like this. And this is so simply to make it aesthetically appealing to the reader, and there's no law that you have to do this and make a square rectangle, but that kind of makes it neater. So this is what's given to us. So the first step is that's a given information. All right. Now basically you're solving the equation, but then you have to give a reason for everything that you do. Well, in solving this equation, the first thing that I'm going to do is I'm going to add 3 to both sides like this. Okay, so from algebra we learned that that's kind of how you do things, right? Okay, so if you add 3 to both sides, what you arrive at is this: 2 times the quantity x plus 5, and then basically adding 3 to both sides, you get this is gone here, and then you get 16, right? So you get 16. So that's where you're going to arrive at. Now, why can we do this? Well, the reason we can do this, and I hope you appreciate, is why. Well, if you said this is because of the addition property of equality, you would be correct, because in addition property of equality states that if A is equal to B, and right, if something is equal to something else, then you can add something to both sides, and that would be okay. So that's the addition property of equality. So the reason for this step being a legitimate step, the reason we can say this over here like this, is because of the addition property of equality. So let me write that down. So addition property of equality. So for real numbers, this is all real numbers, we're assuming that here. So, and then what do you do next? Well, if you wanted to solve this, well, you can do a couple of ways actually. You can actually distribute this, right? That's one way of doing that. That would be okay too, because in algebra there's more than one way of solving equations, correct? But here I'm going to divide both sides by 2 like this, see? So I can divide both sides by 2, and if you do that, on the left side you have x plus 5, and then it's going to equal to, if you divide 16 by 2, you get 8. Okay, so that's pretty good. Now, what's the reason that I can do that? Why is it why is it legitimate? For me to do something like that? Correct? Well, it's legitimate because of the division property of equality, right? Because the division property of equality says if A is equal to B, then A divided by C is equal to B divided by C, provided that C does not equal to 0. And clearly C is not 0, because here you're dividing by 2. So this step is very legitimate, and I can do this because of division property of equality. And finally, I can subtract 5 from both sides, and I can get x is equal to subtract 5 from both sides of the equation, and x is equal to 3 over here, like this, right? So, and what is the rationale for this? Well, there's a reason why I reviewed all them properties here, and the rationale for that, of course, is subtraction property of equality for real numbers. So because subtraction property of equality says is if A equals B, right? If A is equal to B, then A minus C is equal to B minus C, like this. Okay, so, and hence we have proven that that if this given information is true, then we can arrive at this particular conclusion that x is equal to 3, right? So And this is an example of a flow or a paragraph proof. So in a flow, this is an example of a flow proof. In a flow proof, you write the given information and you write what you're trying to prove, and then you draw what's called a flow diagram like this. In this case, this is an example of a algebraic flow proof, ALGEB, algebraic flow proof, because we're using basically algebra, solving algebraic equation. We can have geometric flow proofs also, and which I shall show you in just a second. So, and then you draw what's called a flow diagram flow proof. So you start with the given information, and at each step you write why your step was justified, and until you arrive at your conclusion. So this is one example of a flow proof. Okay, so here's a geometric example. First, let us read the question. The question says, given that Q is the midpoint of PR, so here's Q, and we're told that it is the midpoint of PR, segment PR right here. Okay, that's the first part. So given that Q is the midpoint of PR, and then we're told that R, which is here, is the midpoint of QS over here, and so we're asked to prove that PQ is, which is over here, is congruent to RS over here. Okay, so, and there our instructions are to write a flow proof and a paragraph proof here. So we asked actually to write the same proof in two different forms, and a flow proof, which is like a diagram proof as we did last time, and a paragraph proof, which I shall introduce to you next. So let's reread this question and see what we have. So given that Q is the midpoint of PR, so if you're given a diagram like this, you can basically write on it and think to help you think through the problems. So Q is the midpoint of PR. So if Q is the midpoint of this particular segment, it means that this segment PQ is congruent to QR like this, doesn't it? That's kind of what a midpoint is, right? And then R is the midpoint. R is the midpoint of QS. So if R is the midpoint of QS, then that means that QR is congruent to RS. I mean, this is congruent to this, correct? Okay, that means they're all kind of congruent to each other anyways, and then it's easy to see, at least visually, that PQ is congruent to RS, because if this is congruent to this, then that makes pretty good sense to me. So how do we write this as a flow proof? So in the flow proof, if you remember, the first thing we do is we write the given information. So here we go. So we write the given information like this. Given information involved, in this case I'm just going to write all of this. So this is all the given information to us. You would rewrite this, and then we would say this is what we are asked to prove. So we are asked to prove that. Okay, so where do we start? So let us start with the given information. So I'm going to write the flow proof. Okay, so here is my flow proof. Ta-da! It's going to require a certain bit of work, I can tell right now. Okay, so start with the given information. Okay, Q is the midpoint of PR. So I just write that Q is the midpoint of PR. Okay, segment PR. So that is given. And from I can also write the second one if I wanted to. R is the midpoint of QS. Okay, so, and then I can rectangulate this. I love rectangulating here like this, and I can say this because this is the given information. So that's given to me. That's kind of funky. My handwriting is not the best, I get it. So here's given information. Alright, so Q is the midpoint. So I can say that because that's given information. But my arrows are cool. Well, here we go. And from this, I can say, from this, I'm going to be able to say the following. Well, if Q is the midpoint of PR, then I can say that PQ, right, is congruent to QR. Okay? And I can also say that QR is going to be congruent to RS like this. Okay, why can I say this? Okay, well, first I can rectangulate this because it's just kind of looking cool. So I have a pretty good rectangle. So why can I say this? Because this is that's what it means to be a midpoint. This is actually the definition of midpoint. A midpoint is a point that divides a segment into two congruent segments, or two congruent segments like this. Okay. Alright, so what can I do from here? Well, from here, I can say, okay, watch this. This takes a little bit of getting to know how geometry proofs work, actually. So you have to do this enough times to kind of memorize the logical steps here. So, so stay with me. So from here, I can say that PQ is equal to QR. So PQ is equal to QR. And I also said that QR is equal to RS. Okay. And then I can promptly rectangulate this like this. And so I just taken the congruent statement and wrote them as equality statement. And the reason I can do this is because this is the definition of congruence. That's what it means for two segments to be congruent, that their measures are congruent. Okay. Now, why do I do this? Because I know only so far I only know properties of real numbers. Okay, I only know properties of real numbers. I do not know properties of other things yet. Okay, so fine, I know this. But now you see PQ is equal to QR, then QR is equal to RS. That sounds familiar to me. If it's A is equal to B and B is equal to C, then A is equal to C, doesn't it? And that's like transitive property of equality for real numbers. So I can use the transitive property of equality because we're talking about real numbers here, because these are measures of segments. So since we have something that's overlapping here, something that's common to both of these statements, I can say that PQ is going to be equal, the length of PQ is equal to length of RS, like this. Okay, so why can I say this? Well, because of the transitive property of equality. Because of transitive property of equality for real numbers. That's the transitive property of equality. So, and am I done here? No, we're not done here, because the question had asked to prove that they are congruent. It didn't ask me to prove that they're equal. Well, that's easy enough, because then I can say PQ is congruent to RS like this. Why? Because, darn it, that's the definition of two segments being congruent. So definition of congruent segments. Two segments are congruent if their lengths are the same, if their lengths are equal. So that's an example of a geometric flow proof. Now, what is a paragraph proof? A paragraph proof is really same thing, except you kind of have to type it out, write it out. So in this case, you basically you would put all of this thing in a big paragraph. I'm going to type it up and I'll show you how that goes. Okay, so it's no different than the flow proof, but except it doesn't have the pretty rectangulated diagrams and the arrows, etc. So all of this written out in a paragraph form would be a paragraph proof. And here it is. So I have basically typed this whole thing out in words. So I said proof is the following. The paragraph proof is simply the flow proof in words. I said if Q is the midpoint of PR and R is the midpoint of QS. So Q is the midpoint of PR and R is the midpoint of QS. Then PQ is congruent to QR, like this. Okay, this is the so start out with the given information. Okay, if Q is the midpoint of PR, R is the midpoint of QS, then PQ is congruent to QR and QR is congruent to R. Basically what I have given over here. And the reason for this is the definition of midpoint, just to have stated over there. From this, it flows that PQ is equal to QR and QR is equal to RS. This is because of definition of congruence. And from there, by transitive property equality for real numbers, PQ is equal to RS, and that's this over here. And by definition of segment congruence, PQ is congruent to RS. So this is an example of a paragraph proof. Now you can see now the merit of a flow proof, because you can kind of visually see this as you kind of think through the problem. And paragraph proof, and it can get kind of complicated. Just looking at it kind of threatening in a way, isn't it? So, but they have their merits. They basically tell the reader how you come to a conclusion. And there's a third form of proof, as I suggested, and that's called a two-column proof, which kind of takes the best of both of these and puts them together. And inshallah, we shall talk about that in the future. Until next time, as-salatu was-salamu ala rasulillah walhamdulillahi rabbil alameen. Assalamu alaikum.